I had asked that I told that I'll record. I did not start the recording. So, and this is something very, very important. So, this is one parameter that you look into in order to understand how good the structure is. So, as I said, lower the resolution is, better resolve the structure. Numerically lower the resolution is, better resolve the structure. So, this is 1.6 angstrom, and this is really high resolved structure. Now, when you're trying to determine the tertiary structure, as I said, what happens in X-ray crystallography is that you obtain the diffraction spots, convert into electron densities, and then you fit the protein backbones with the side chain on the electron densities and determine the atomic coordinates or the positional coordinates of every single atom or as many atom possible in the protein tertiary structure. However, it may happen that there are certain residues for which you do not have any coordinates obtained during the diffraction. Okay, or essentially, what it means is that you either the atoms or the backbone on which of the backbone itself was so highly mobile that there was no unique there's no unique electron density that one can obtain, and hence you cannot fit any one single conformation in order to tell you what would be the structure of this part. And this constitute many times in protein tertiary structure, which refers to something called as the missing residues. Okay, and in fact, it's very interesting is that people, I mean, kind of literally ignored missing residues, saying that they are very high mobile region of a protein. In a sense, they are too flexible, and hence you really don't care about this missing residues. Keith Dunker, who started the area of intracellular disorder regions, was actually focusing on this missing residues and was asking the question, why do you have this missing residues? And while analyzing these missing residues, he did start the whole area of intracellular disorder. So, I mean, many times the information which people ignore could be very important to for later studies. So, what you'll find is that you will have the information of what residues are missing in the PDB. And when you are looking at a structure, what you can find is that there will be a gap in the visualization which you can see, and then it tells you is that whether there is a missing residue in that particular protein tertiary structure. So this is just telling you what are the missing residues in the protein tertiary structure.
Sir?
Yeah.
Sir, by this do you mean that the structure actually keep on changing? That is why we are having these kind of missing residues?
So what happens is that when you're if you have suppose you have this kind of a confirmation, okay, and this particular confirmation suppose ends up in having multiple possible confirmations, right? So one confirmation, then next confirmation. So because it's moving or it's highly mobile region, the electron density that you'll be getting will not be something very uniform. Rather, it will be completely messed up. Okay, and hence because it's completely messed up electron density, you will not be able to fit in one single confirmation to this. And since you're not able to fit a confirmation, you will say, well, I don't know what confirmation to say for this, and that's what gives rise to the missing residues. Yes. So to answer your question, it's essentially because that particular region is highly flexible, and the electron density, you have electron densities, but the electron density is no more kind of can be fitted by any one single confirmation, and that doesn't give rise to this missing residues. Any question anyone has? Okay. So and then PDB, I mean, the people who are studying the structures are also analyze what kind of ligands are bound and what are the ligand binding sites and so on and so forth. And this information is also deposited in the PDB. So you'll find certain software mention what uses, what was used to determine this binding site and so on. Now here I'd like to remark two things. I mean, one is that when in solving a structure, okay, many times you not only solving when you crystallize a protein, you don't, I mean, you need a very high concentration, you need certain compounds, a certain chemical compound in order to concentrate and start seeding the crystallization itself. And for example, PEG is one such certain compound. You have water which is bound to your protein. You can have something else bound to your protein. So when you are solving a structure, you not only solve the structure of the protein. However, apart from this, you also solve the structure of anything that is bound. It could be PEG, it could be any metal bound to it, it could be any chemical compound bound. So many times what people, I mean, anybody who's trying to understand an enzyme and say what kind of substrate it bind, where does my cofactor bind, what they do is they solve the structure, they crystallize the structure, and then put into a X-ray, put it through the X-ray beam, and then they take this particular crystal and then soak in the soil in their desired compound, whatever they want to solve it with, and then the hope that this compound will occupy its binding site in go and bind, and then can give you the structure of the compound bound to the protein also. So the crystallography used various kind of technique in order to get this, apart from protein, something bound to it. It could be a compound, chemical compound, it could be DNA, it could be RNA, it could be your water. So anything which is not a protein, okay, are called as heteroatoms, okay. And when you're looking at a particular protein tertiary structures, you not only are getting protein that you are interested in, but also hetero compounds or the heteroatoms, which are the something else that is bound to a protein. And these are the things which are defined by the authors themselves. So suppose I'm solving the structure of a DNA. So when I'm solving the structure of a DNA, DNA cannot be a heteroatom, because the structure I'm solving is for a DNA. So what will happen is that when you solve a structure for DNA, the DNA will have will be the main compound that you are solving the structure for, and anything else bound to will be called as an heteroatoms. Okay. So in this particular case, this is a citric acid, and then you see this is the heteroatom that is bound to the protein is called citric. And then not all the time, but you will have another thing which is also mentioned in this PDF file format, and DBRef essentially says that there is a database reference for something. So database reference says that this is the PDB, and this is database reference to UNP is UniProt, which I hope you are familiar with. So UniProt is a database, is a repository of all known protein sequences, and this is the identifier. Just like I said, there is a name required for your protein tertiary structure. Similarly, there is a name required for protein sequences, and this is a UniProt unique identifier, and this is UniProt extended identifier, which tells you in some detail what this protein and what the organism it comes from. This part is the name of the protein, what this protein does, and this part is the name of the organism, where it comes from. So if you do it analysis, then you can actually use this such a detail to understand what it is. Now the question is, and this is something very interesting, is that do you have UniProt for every single PDB identifier? What do you think? Anyone? Do you think you will have a UniProt identifier? Sorry?
The PDB is only giving us the structure, right?
Correct.
So we can't say actually that from the whole structure we know all the amino acids. I mean, they must be knowing, but not exactly all the amino acids can be I mean, recognized, as you said about the conformation also, right? So in that
Correct.
case, we
So
can't say.
My question is slightly different. What I'm saying is, what I'm asking is essentially that if I give you a PDB identifier, should I be able to tell you what protein it is for? Right? I mean, I should be able to reference, right? In all practical sense, I'm solving the structure. I know what protein that I'm dealing with, and hence I should be able to tell you ideally speaking, for every single PDB identifier that I have, I should be able to have an equivalent UniProt identifier to it, right? Because you know what protein structure you're solving for.
Yes, we can have. I mean,
right, but
have identified.
unfortunately, this is a nightmare for anybody who is dealing with this particular issue. Very early on, what people used to do is they will, and this was very common mistake. So suppose I am trying to solve a structure, and all things done very diligently, I purify, crystallize, and do everything. And when I go and look at the structure, what I solved for, actually the many times the structure is solved for lysozyme or for some other protein, which is, and this happens because of the contamination that takes place. So quite number of lab used to study, and this is quite a early 2000s. People used to study lysozyme because this is one of the protein which you put it wherever you feel like and it will crystallize. Okay, so people used to study crystallization of lysozyme. So what used to happen is a cross contamination, and your protein goes along with lysozyme. Lysozyme will crystallize, but your protein hasn't crystallized. Okay, and then what you determine the structure is of a lysozyme. You go and deposit the structure in the PDB. PDB will accept it, saying, well, it's excellent. It says you have a structure, but the structure is completely of a lysozyme. And this error kind of took very long time to get rid of from the PDB. And finally, what you end up in having is that you have solved a structure for a protein. You don't tell what uniprot you have solved a structure for. You go and talk about all protein that you want to give detail for. You will have you go and read the paper. They'll tell you exactly what protein they're talking about, but they will not tell you what uniprot identifier they solved the structure. Okay, and hence what actually happens at the end of the day is that literally, I mean, it's a struggle for really mapping the PDB file to a uniprot protein sequence, even though you have a structure for a protein sequence, but you really don't know what protein sequence you have a structure for. So this is kind of ongoing battle between trying to establish a unique uniprot identifier to a protein structure. This also is a kind of a problem because in solving a structure, some protein needs addition or make it chimeric with some other protein. So for example, if you're trying to solve structure for membrane protein, you end up in combining with some kind of antibody such that you're able to crystallize. So membrane protein doesn't usually crystallize in solvent because they're trying to keep away from solvent, especially in membrane spanning region. So they will have antibody bound to it, and when you make want to bond the antibody, you will actually make it chimeric protein, and hence for a uniprot for a PDB identifier to say this PDB identifier corresponds to uniprot sequence doesn't remain a problem which is very simple to resolve. So this is one problem that you may face. So don't assume always directly that for every PDB identifier you have a unique uniprot identifier. Many times if it's not there, don't be surprised. You know why it may or may not be there. Then there is something which is known as sec-ed record, and this is the conflict between the sequence for which you think you are solving the structure for and what you see in the electron densities. Okay, and so this is just to show you an instance. So for 2VEK, the position 15 is known as serine. However, the protein, the amino acid known at this position is asparagine. Okay, now you say, I mean, how is it possible that I end up in having asparagine is in my sequence, but I have serine in my structure? Now there are two explanations for this. One is that my protein is if it is a mutation, and it's I think it's mentioned over here. So this is an engineered mutation. So I have made alanine at this position 233, and hence you end up in having, of course, because you did design it, you end up in having this clash between the residue at 233 alanine to 233 valine. So in sequence this is valine. In this in structure this is known to be alanine. Apart from this, what happens is that when you're solving a structure, you're not necessarily looking at the sequence that you are solving a structure for. Okay, what you have is that you have electron densities, you fit whatever the side chain that can fit in the particular electron density, and in doing so, you may end up in fitting electron density of completely different amino acid at that position, because that's what gets fitted. Okay, and this give rise to this conflict that you end up in having, for example, aspartate and this is glutamate. And this conflict is quite common with glutamate and glutamine, aspartate and asparagine, because there's only change of CO and NH. So in the side chain, and that gives rise to the quite a common conflict between projects. Then there is something record called sec-res record. Now the set rest record is the sequence which the author thinks they are the solving structure for. Okay, and this is a set rest record which is deposited in the PDB. I've already mentioned about this head or hetero atom. So this is simply called as HET, head, and this is called hetero atom name. So het is the name of the compound for which is not protein atom in a protein crystal structure, and in this case this is citric acid. What is the name of this particular compound? This and they it's essentially is a 3-letter code. I'll just tell you why this is a 3-letter code as I go along. So this name of this particular compound, as if keep mentioning before also, is citric acid, given by 3-letter code CIT. Authors also deposit what kind of secondary structure it has, so helix and so on and so forth, but not necessarily that you're going to look into it. Okay. The other and the most important detail that is, you really want from tertiary structure is the positional coordinate of the atoms that is present in the protein tertiary structure. Okay, so this is the information which is present in this particular format. I'll go over this. So you have, this is total number of columns what we defined over here. Every single atom coordinate start with this 4-letter atom, and it ends, the whole polypeptide chain ends with a record called as TER record. Okay, so TER record is a record which tells you that one polypeptide has now finished in the PDB file, and the next information that it starts will be the record for the next polypeptide or for a heteroatom. So so this is the record part that I'm mentioning about. For the heteroatom, the name is called het atom, HET-ATM. Okay, so this is the 6-letter code. So the first 6 position get occupied for the information of every single atom, what it has. And then you have another I think 6 positions which are dedicated for simple increment of the count 1, 2, 3, 4, and absolutely has no meaning whatsoever. Then you have something, what is the atom type? So you have, when you are looking at a polypeptide chain, then you have the backbone, which is defined by your N, C alpha, right? C double bonded O, right? N, and keep continuing in this, right? So this is what you have described as a backbone. So this N, C alpha, C, O refers to the backbone atoms N, C alpha, C, and oxygen to carbonyl oxygen. Okay, and then for every single C alpha, you will have the side chain, right? It could be another, for example, for alanine, this will be C, and this is 3H. So this next C that is referred apart from C alpha, they are given by name C beta, or simply written as CB in the PDB files, or anything that is attached to C beta will be given as extension as H beta, and so on and so forth. Then there will be C beta, then after C beta, anything attached to C beta will be given as C gamma, or simply written as CG. Anything that is attached to C gamma will be given as C delta, given as CD, and then C epsilon, or the CE. Okay, so they are different. That's how the naming happens with the sites. So this is the information which is present in the next 4 columns, and then you have information about what is the amino acid, and this is a typical 3-letter code which is used to tell you about the amino acid. In this case, this is SCR serine, and as I said, and that's the reason that heteroatom, in order to maintain the format, this is also given a 3-letter code for the heteroatoms, and this is CIT for the citric acid. And then you have the chain identifier information given. So chain identifier, as I said, refers to one polypeptide in the PDB file. Okay, and then you have the most critical information that is present from this point onwards, is that apart from chain, you have the residue ID. Okay, this is called as the residue ID. or residue identifier. Now this residue identifier, if you look at it, then one can say that this is a serine 2 present in the protein sequence, whatever I have observed, whatever structure that I am solving for. Unfortunately, that is not the case. Okay, this assumption, even though this says that this is residue 2, it may not correspond to residue 2 position in the protein sequence. And this is something that you should kind of, anytime you're dealing with the protein structure, you look at residue ID and think this is my residue 2 in the protein sequence. You should not directly assume it. It may be completely incorrect. When you solve the protein structure, okay, using, and we go through this stage of refinement using a program which is called O in crystallography. These residue ID assignments are completely done in by the program. It's not really intervened by a human and saying that no, I want to call this residue 1 and so on and so forth. And what you can actually end up in having is, by residue can start with minus. Okay, and if you think of it, I mean, what do you say, residue ID -1? There's nothing called residue ID -1. So you can imagine them to be a placeholder in order to tell you the directionality of your polypeptide sequence. And don't try to infer too much from it. If you want to know what it is, you need to align the sequence of the atom record, that is in the atom records section, to the sequence of the protein that you are solving for. And based on it, you can say what is the equivalent residue ID of 2 in the protein sequence. And after this, so this is something which you should always keep in the mind when you're dealing with the protein tertiary structure. After this, you have the XYZ coordinate of the every single atom that for which you could obtain the reliable electron densities. Okay.
Sir?
So yes.
So can you repeat about the residue ID?
Okay. So residue ID is a 4-column assigned to it, and this residue ID you can consider it to tell you about the continuity of the protein residues that you're seeing in the structure. Okay. Don't consider. So even though this looks, this is residue ID 2. So this residue ID 2 does not, it may not correspond to the residue 2 in the protein sequence. Okay. So for instance, I mean, if you see over here, I mean, so if you see this over here, the first residue that you have is serine, right? Second residue is lysine. However, in this particular residue ID, you see this serine has a residue ID of 2. Okay, so this serine, even though in the sequence this should have been first, this should have been ideally been numbered 1, but this is not numbered 1. And I told you the reason. The reason is that crystallographer take the electron density, feed to a program, and then program decides that what number does it want to give. Does it want to give 1? Does it want to give 2? Whatever it is. I mean, in fact, this number in some of the PDBs you'll find this residue ID number starting from -1000. Okay. Now -1000 is not a residue ID. I mean, residue ID is kind of telling you residue position in the protein sequence, but -1000 has no relevance. I mean, in terms of its position in the protein sequence, and hence it has no meaning. So what I'm trying to tell you is that you can consider them to be a placeholder to tell you about what sequence, what residue comes from what residue in a protein tertiary structure. Whether there is a break in the protein, that certain residues are missing, and that's what it should be used for. And don't try to over infer, and don't try to read too much into it, saying that this is residue 100, and this. Suppose you find something, there's a conformational change at residue ID 100, and then you claim, oh no, residue ID 100 of certain, let's say, phenylalanine is changing conformation, and you go gaga about it without trying to understand whether this phenylalanine residue 100 really correspond to residue ID 100 in the protein sequence. And because when experimentalists give you the data, they tell you the mutations, any change that they do with respect to sequence which you see in the uniprot, right? But when you look at the structure, that residue ID which experiment is referring to actually may not be this particular residue ID you want to see in a protein tertiary structure. And I'm just trying to caution you and keep in the mind when you're dealing with this particular thing. Is it clear?
Yes, sir.
Okay. So then is the information of the XYZ coordinate. This is the present something in the orthogonal space. So if you can imagine any 0, 0, 0 in an orthogonal space, and this XYZ coordinate is a positional coordinate in such an orthogonal space. So and this is typically has a format of, if you are familiar with little bit programming, this is a format called 8.3f, essentially, which means there are 8 positions given to store this XYZ coordinate. Of this, 3 positions are dedicated for the part which is coming after decimals, and hence you will see this given to 3 decimal places, and whatever comes subsequently to it can be filled into it. So this is the format which is given, and then the XYZ coordinate which is given for every single atom, and that's what you are interested in. Right? So this is the positional coordinate with respect to some 0, 0. Okay, so I can have 2 protein structures which are lying in the same space in some orbit 0, 0 space. Okay. Then there is a factor which comes quite often, is called occupancy factor, and then the B factor. So let me tell you about occupancy factor. So when you determine the tertiary structures, what can happen is you can end up in getting, imagine that there are 2 entirely distinct conformations of certain site chain. And just think for a moment that half of the protein in the crystal has one conformation and half of the protein in the crystal has another conformation. Now, if such a thing happens, you end up in getting electron densities not for one conformation, for both the conformation, because half of the side chain is in one conformation, half of the side chain in another conformation. I hope I have an example. There it is. So you see, this is an arginine side chain, and what you see is that there are 2 distinct conformations of the arginine side chain. And what you are looking at is the 2 electron densities that are generated because of these positions. What you see, mesh-like structure is essentially the electron density of these atoms. So you have 2 distinct electron density generated, and they're 2 distinct conformations. And once you have such information, this is what is put into this factor called occupancy. Occupancy, as the word says, this is how frequently that a particular atom occupies this position. One means one single conformation. That means this is XYZ coordinate, that's it. If I have multiple occupancies, so I can have not 1, I can have 2, I can have 3, at most 4 conformations. So that means the atom can have 4 distinct conformations. Okay, I want to make this very, very clear. There are 4 distinct conformations, one which can be distinguished from each other. So and if that happens, then this occupancy will take in value of 0.25. If it is 3 conformation, distinct conformation, it will be 0.33. And you look at how frequently do you find them. If they're equally distributed, then they're 0.33. If they are not, then one of the conformations will have a higher occupancy number. Okay, so you will typically have 1, and then if it is not the case, then you will end up in having a lower occupancy numbers. What it tells you is that there are 2 distinct conformations. Why do you worry about it? Many times you are dealing with a structure where there will be multiple occupancies, and if you have multiple occupancies, maybe one conformation is what you're interested in, second conformation you're not interested in. So you can study from, maybe the 2 conformation give rise to certain effects, and you can, many times people don't really care about it. You take one conformation, and because both are equally populated, it really doesn't make much difference in analysis. There's another factor called B factor. Okay, this is also known as Debye-Wally factor or temperature factor. B factor, temperature factor, Debye-Wally factor. So what it tells you is that this is usually used to describe the attenuation of the X-ray scattering, okay, which is caused because of thermal fluctuations. And just to give you some understanding to it, suppose I have an atom and it's really, it's not moving, it's completely rock solid static position, then you will end up in generating electron densities which will be very, very stable. Okay, it's kind of a spherical electron density that you end up in having. Okay, however, if you imagine this atom is kind of moving in all 3 possible directions, what will happen is that the electron density that you're obtaining now may not be exactly like this. Maybe it end up in having electron density which will go like this. Okay, or what is known as smearing of an electron densities. So because of the thermal fluctuation of the atoms, that's one of the reasons which is assumed. The thermal fluctuation atom, and you are assuming this to be isotropic. That means they are moving in all three orthogonal direction in the same frequency. And this gives rise to a smearing of electron density. And compared to a standard electron density which could obtain for a static atom, this is not correspond to it. Okay, and hence you can think B factor is kind of a term which is used in order to adjust for the smearing, and in some sense this smearing that you are getting is because of thermal fluctuations. Apart from thermal fluctuation, actually it incorporates also if your backbone is also moving along with the thermal fluctuation. So what it gets interpreted as, and the B factor is an experimental parameter, is actually is a fitting parameter in the crystal structure. And this tells you about the flexibility of that particular atom in the protein structure, and this is specific to a protein structure. You cannot compare B factor of one protein to another B factor of another protein. This can range from your anywhere between 10 to any higher number. Not really, it doesn't have any specific boundary. It can become 100, 200, whatever the number it may be. And the higher the B factor is, in understanding, the higher the B factor is, this is given in angstrom square. And the higher the B factor is, tells you that the particular atom or the region where this particular atom is sitting is highly flexible. And in fact, there are a lot of studies which are done which have tried to correlate the flexibility of a protein by looking at the B factor. Lower the B factor is, more rigid the structure is. So that means if I'm looking at a particular protein structure, I can, if I want to understand what part of the protein structure is flexible in comparison to each other, not trying to compare to another protein, then you can use a B factor and look at the B factor which is very low B factor, you call them to be rigid regions. High B factor region, you call them to be flexible regions. Okay, so this is something, another parameter which you worry about it. So occupancy, B factor, also something that you should understand when you're looking at the protein tertiary structures. There is a record which tells you the termination of one polypeptide. If there are multiple polypeptide, every single two polypeptide need to be looked into it. This TER record is important because what happens if you do not have a TER record, then you will end up in getting a very continuous chain, and very old visualization software used to have this problem, is that you end up in getting a, if you have two chains, they basically will try to join two chains, and it looks very odd. You end up in getting completely incorrect structure in visualization. Then you have a detail of this head atom. Same way that you have details for atom, you also have detail for head atom record. It also have its own atom names, 3-letter code for the compound which is solved along with this, and this numbers, what you see corresponding residue IDs, really do not have much meaning, because it follows a certain order to arrange atoms, and this, how these atoms are connected, is given another information I've not shown over here. It's called connect record. Okay. Again, they have XYZ coordinate. You can analyze this XYZ coordinate to find where they are lying in the protein tertiary structures. So this is for X-ray structure, what you see. In case of NMR structures, you have another two detail which gets into it. It's called model. Okay. So you'll end up in having every single coordinate actually start with something called as a model. Okay. Yes. Okay, so it starts with model and say model 1, model 2, and so on and so forth. Okay, so typically, as I said, NMR, you are fitting multiple models, you have multiple structures. So you will have one model, model 2, model 3, and so on and so forth. This is one such confirmation I should have maybe after this. Yeah. So this is NMR structure. You see there are multiple conformations, and each of these conformations are called as model in a PDB file. So with this, I'll finish about the PDB file format, which I want to talk about. What we can do is we can take a break. It's really long. I didn't want it to go this long. And maybe when do you want to assemble? To look at UCS of Chimera. So what I want to do is I want to finish with the visualization part of it, and then go on to talk about the analysis in the series of videos that I'm going to upload. You want to upload, you want to assemble at 12?
Sure, sir, that works.
Sorry?
That works.
That works? Okay, so
Yes.
we'll take a half an hour break. I mean, you must be really tired of looking at the screens for such a long time. So we'll take a half an hour break and assemble at 12. And then
Um,
just a question, all of you have downloaded UCSF Chimera?